Hello, my name is Sam Ord. I'm an ICU doctor at Nepean Hospital in Sydney, and this is a series of lectures on ultrasound physics, and it's particularly aimed at candidates trying to undertake a more advanced qualification in ultrasound. So in this first section of lectures, we're going to be talking about physical principles of ultrasound, and this is going to be done in three parts. In this first part, we're going to discuss ultrasound and its propagation in tissue. The objectives of this lecture are to discuss the nature of ultrasound, how the ultrasound sound wave propagates or moves in tissue, and finally, how the sound wave gets attenuated or loses some of its intensity or power as it travels through those tissues. So what are sound waves? Well, sound waves are mechanical compression waves which are parallel to the direction of travel. So if we were to consider a group of particles which are being affected by a sound wave, and we were to consider how the pressure varies over time, we're going to see that as the sound wave progresses, you will get the particles being pushed together or compressed, and then they will be stretched apart, which is known as rarefaction. So as the sound wave moves, it's moving parallel to the direction of travel, which means it's known as a longitudinal wave. And this is in comparison to something like the ocean, where the ocean particles move vertically, and it's known as a transverse wave. So ultrasound waves are essentially just high-frequency sound waves. And what we mean by that is frequency is the number of cycles per second, which is measured in hertz. So for hearing, you have between 20 cycles to 20,000 cycles occurring per second, which is 20 hertz to 20 kilohertz. Ultrasound is typically anywhere between 2 to 15 megahertz, or 2 to 15 million cycles per second. If we were to consider an individual sound particle and how that sound particle oscillates over time, we're going to get the variations in pressure. And this is where we get this characteristic sinusoidal movement that you see here in this graph. And as we get the compression and rarefaction, the pressure is obviously changing, and the maximum variation in that pressure from mean is known as its amplitude. And this determines the amount of energy in the ultrasound wave, which is the power and the intensity. And we'll discuss this more later in this lecture and in other lectures. Considering the pressure over time, we can consider the time that is occupied by one cycle, or one compression and rarefaction. And this is known as the period. And the period is related to the frequency as it is inversely proportional to it. So that if we consider, for instance, a 1 megahertz ultrasound wave, that takes 1 microsecond for one sound wave. Instead of considering pressure over time, if we was consider how the pressure varies over distance or depth traveled, for instance, we can now get an idea of what the distance occupied by one cycle is in terms of the wavelength. And if we combine both of these two figures, both the pressure over time and pressure over distance or depth, we can get an idea of what maybe the velocity is of the sound wave. And if we remember the equation, velocity equals speed times time, we can then get an idea of what the propagation velocity, or the speed of which the ultrasound wave is moving through the tissues, and we can say propagation velocity is equal to frequency times wavelength. And then, for instance, for an example, if I were to tell you what the frequency of an ultrasound wave was, and you were able to assume what the speed of that ultrasound wave was traveling through the tissues, you could then determine what the wavelength was of a structure by rearranging the equation so that wavelength equals velocity divided by frequency, for example. The typical diagnostic ultrasound frequencies range between 2 to 15 megahertz. And what you can see from this table is that as the frequency increases, wavelength decreases. And I think it's also important to notice that for all frequencies in diagnostic ultrasound, you can see that the wavelength is generally less than 1 millimeter. And I guess that's important to try and remember when you're trying to answer questions, for example. If you're seeing a wavelength that's 2 centimeters, you can start figuring out that's probably you've got something wrong with your calculation. So trying to remember that all wavelengths for diagnostic ultrasound frequencies are generally less than 1 millimeter helps just provide a bit of a guideline when you're doing your equations. Now, as we're going to discuss later, the resolution of the ultrasound image is directly related to the wavelength. The smaller the wavelength, the better the resolution. But this comes at a price, because for higher frequencies, you're going to get greater attenuation. And with greater attenuation means that you're not going to be able to image as far into tissues. So a constant balance is being played between trying to get the best resolution and the right depth. And that's where we have to remember that the higher the frequency, the better the resolution, but you may not be able to get as good a depth in your analysis. The propagation speed of ultrasound in tissues is dependent on the tissue's density and stiffness. And this means that sound waves are going to travel at different velocities through the different tissues. So for an example, in fat you're going to be traveling at 1,450 meters per second as compared to muscle, for example, where you're going to be traveling at 1,600 meters per second. The problem comes in the fact that the ultrasound machine doesn't know what kind of tissue you're imaging through, and so it has to make an assumption. And so it picks somewhere in the middle of the road, which is the soft tissue. So the ultrasound makes an assumption that the speed of sound that the ultrasound wave is propagating through tissues is always 1,540 meters per second. It's a really important number to remember because it's asked again and again, so that you can determine things like the wavelength of an ultrasound, or how far a structure is away if I gave you a certain amount of time that the ultrasound took to return to the transducer. So it's important to remember that the ultrasound machine assumes that the ultrasound wave is traveling at 1,540 meters per second. So let's ask a question. So what is the wavelength of a ultrasound transducer that's operating at 15 megahertz? So if we remember that the propagation velocity is equal to the frequency times the wavelength, and we remember that the propagation velocity is assumed to be 1,540 meters per second, and for a 15 megahertz probe, we're going to try and determine the wavelength in millimeters. Now, the first thing I hope you can see is that we've got different units being used. And there are obviously different ways of trying to do this. The simplest way that I've found, and this is what worked for me, is I actually wrote out all the zeros. So that I rearranged the equation first of all, and I said that wavelength is equal to the propagation velocity divided by the frequency, and I'd then write out all the zeros, so that I'd put the 1,540 meters per second, I'd put that into millimeters, I'd put the megahertz into just hertz, and in that regard I could then determine what the wavelength was in millimeters. So it's important to remember that velocity is equal to frequency times wavelength, and remembering that typical values are somewhere in the region of 0.1 to 1 millimeter. Okay, so let's consider another question. So if I increase the frequency, what is this going to do to the wavelength, the period, and the penetration? And hopefully from the last few slides you'll be able to determine that as I increase the frequency, that means the wavelength is going to decrease. If there are more cycles per second, that is going to decrease the wavelength, or increase the number of cycles over a certain distance. If I have more cycles, it's going to be a shorter wavelength. If I have more cycles per second, that means that the time that's occupied by each wavelength, by each cycle, is going to be reduced as well. And as we said, The higher the frequency, the greater the attenuation. So that means that the penetration will also decrease. So next, let's consider the interaction of the ultrasound waves with tissue. And in particular, we're going to be talking about attenuation. So attenuation is the weakening of the sound wave, or the loss of its power as it travels or propagates through the tissue. And this means that we're going to limit the depth that we're going to be able to image. Now, why does this happen? Well, it happens because of heating, essentially, and that's because tissue is not a perfectly elastic medium, and so that with pressure variations, you're going to generate some friction, and that friction is going to be realized as heat. And trying to remember that energy cannot be created or destroyed. If you transfer some of the energy into heat, it means you're going to lose some of the energy of the sound wave. So we can compensate a little bit for this with the machine, and it does this by obviously if you're getting weakening of the sound wave as it travels through the tissue, it's then going to be reflected and picked up back by the transducer. It's going to be weaker, and what the transducer can do is just amplify that to try and compensate for some of the attenuation. And this is where the gain button comes in on your ultrasound machine, where as well as the amplification that is made by the transducer, we can also just try and amplify it up by simply increasing up the brightness of the image, for example. Attenuation is going to be proportional to the tissue type. So, for example, the attenuation is going to be greater in bone compared to soft tissue, for example, because bone's got a much higher density. Attenuation is going to be proportional to frequency. As we said, if you've got a 15 megahertz ultrasound transducer as compared to a 2 megahertz ultrasound transducer, we're going to have more oscillations per centimeter traveled, which means that the attenuation is going to happen much faster with greater number of sound waves that are occurring per centimeter traveled, for example. We also know that attenuation is proportional to distance, in that the further that you travel into a structure, the more particles you're going to have to propagate that sound wave through, which means that more heat is going to be generated so that more sound energy will be dispersed. So the greater distance you traveled, the greater the attenuation. So another way to look at attenuation is consider the amplitude, which is that maximum variation away from the mean. And we can see that that amplitude reduces as we travel down through the distance, or the further we travel. Amplitude and intensity are indicators of the strength of sound, which is it's a bit like the loudness of the sound if we could hear it. Intensity, if you think about the equation, it's just power divided by area, and the way I think about that is, for instance, like pressing down on a thumbtack. Obviously pressing down on the larger surface area means that all the power is then focused in on the point of the pin, for example. Comparing intensity with amplitude, it's proportional, and intensity is proportional to amplitude squared. If we want to try and describe attenuation, we talk about it as the ratio in the change of the intensities. And we can say that attenuation is measured in decibels, which is a logarithmic scale. And what I mean by that is that if we use a logarithmic ratio of powers, we can try and describe a ratio in smaller numbers. Because actually when we talk about attenuation between the transmission and the reception of sounds, we're talking about huge changes in ratios, somewhere in the region of 10 to a million change in intensities. And in that regard, we have to use a scale that is a bit more user-friendly, and this is where the logarithmic scale comes in. And this graph is meant to try and help describe some of that, because I can find it slightly confusing at times. So if we consider a change in decibels, such as the green line, and if we have a look at the change in the intensity for 1 centimeter traveled, we'll see that it's about halved. And that's a 3 decibel drop. If we consider a tenth, so consider the blue line, for example, that's fallen down to about a 100th of its original intensity, we can describe that as a 20 decibel drop. A 10 decibel drop would be about a 1 to 10. So now let's ask a question. So compare the following intensities in decibels. So if you have intensity 1, which is at 100 milliwatts per centimetre squared, as opposed to intensity in a second, the second intensity, which is 0.1 of a milliwatt per centimetre squared, we can see that we've dropped about 1,000th. Okay, so the ratio is 1 to 1,000. That is a 30 decibel drop. So just to recap, you can see that if it is with a logarithmic ratio of powers, if you have a 1 to 2 ratio, that's 3 decibels. If you have 1 to 10, it's 10 decibels. If you have 1 to 100, it's 20 decibels, and 1 to 1,000 would be 30 decibels. The attenuation coefficient, as we describe it, is how the intensity varies with centimetres travelled. And so it's measured, the attenuation coefficient is decibels per centimetre. Typical soft tissue attenuation coefficient is about 0.5 decibels per centimetre per megahertz. So for example, if we had a 2 megahertz ultrasound wave imaging at 20 centimetres in depth, we can do the equation 0.5 times by 20 times by 2, which equals a 20 decibel drop in intensity. So that means we get about a 1 in 100 loss in intensity by the time a 2 megahertz frequency ultrasound wave has reached 20 centimetres in soft tissue. And what's important to remember is that you're going to get a further 20 decibel attenuation once that ultrasound wave is then reflected. So that means that you're going to get about a reflection, you're going to get a loss in intensity of about 1 to 10,000 by the time that sound wave reaches the ultrasound probe again. And if it was a 3 megahertz ultrasound probe, we're going to get a 1 to 1,000 loss in intensity, or a 30 decibel loss in intensity one way. And that means that that's going to be then a 30 decibel times by 30 decibel. And we're going to get a 1 million loss in intensity by the time that sound wave returns to the ultrasound probe. And so that's the importance of the amplification that the ultrasound machine will make with receiving ultrasound waves. So it's important to remember that the depth of penetration is inversely related to frequency. So let's ask one of the final questions. So, attenuation increases with decreased frequency, increased depth, or bone compared to soft tissue. True or false? So what we can see is that attenuation is going to increase with decreased frequency. Well, that's false. Attenuation decreases with decreased frequency. Well, what we can see is that the depth of penetration is going to decrease with higher frequencies. What about attenuation versus increased depth? Well, attenuation is going to increase with increased depth. How about attenuation in bone compared to soft tissue? Well, attenuation is going to be much higher in bone compared to soft tissue because of increased density. So in conclusion, we can say that ultrasound waves are longitudinal waves, which are compression waves which are moving parallel to the direction of travel. Sound waves are measured in number of cycles per second, or ones of compression and rarefaction. And we're typically measuring those in megahertz, and they're somewhere in the region of 2 to 15 megahertz in diagnostic ultrasound frequencies. If we were to consider pressure over time, for example, the time that it takes for one compression to rarefaction, or one cycle, is what's known as the period. If we were to consider pressure over distance, the distance taken from one compression to rarefaction, or one cycle, is known as the wavelength, typically less than 1 millimeter. If we were to consider speed equals distance times time, we can get an idea of what propagation velocity is in terms of frequency times wavelength. And it's important to remember that equation so that you can reformat it so that you can determine things like wavelength, for example. The ultrasound wave assumes that the ultrasound machine assumes that ultrasound wave propagation velocity is uniform throughout tissue, and it uses the kind of medium number, which is the propagation velocity in soft tissue, which is 1,540 meters per second. We know that with higher frequency, we're going to have smaller wavelengths, which is going to give us better resolution. But the problem with that is with higher frequency comes increased attenuation, and with increased attenuation, we limit our penetration, or we limit our ability to image deeper structures. So that's it. Thank you very much. These are some of the references that I've used to prepare these talks, and I hope it was useful. Thank you very much.